It appears to be making a video, so another draft physics science presentation in this mechanical universe series, so it didn't take them too long to offend again in a sense. So I figure I'll respond to a bit about how they understand the history of the discovery of the relationship between electricity and magnetism. And I didn't think this was very well. It's the same, it's the traditional presentation, and I think it just is misleading, so I will make my qualifications.
In mathematics, Faraday would do as much as anyone to propel science beyond the mechanical universe of Isaac Newton. Newton's law.
So again, it's not like it's obviously Newton can only do so much, so he couldn't provide everything. But anyway, obviously, just electricity wasn't, there wasn't enough of it for Newton to have an opinion.
Of mechanics, together with his theory of the force of gravity, had convinced the world of science that the world could be understood by rational means.
See, they wish to imply that somehow you have to leave the rational realm, and that's what they're setting you up for. That somehow the rest of the universe, it does have wacky bits in it, and it really doesn't have to be understood that way.
Along this same path, Newton's followers would discover that, like gravity, electricity, and magnetism are also forces that decrease with the square of the distance. The similarity was...
Yes, right. So the fact that they're similar for that basic reason, and then when we later found out they all move at the same speed, it really should be an indication that there's no reason to believe they're different forces. That it's all the same thing, just in a slightly different manifestation. That's just such a key. It's the road to unification and the road to making them all rational forces with rational properties.
It's amazing. And to both Faraday and the scientific community at large, it posed one of the significant questions in physics. Whether gravitational, electric, or magnetic, how could any force act between bodies when they weren't even touching?
Right, well, they can't if you don't understand what the word force means. So if you think it's angel wishes, or ESP, or, obviously if you kind of understand it to be particles as they first thought of photons, well, then they're all understandable as what are the particles forcing there to have happen. And gravity is perfectly explained by particles in Mach gravity. And magnetism and electricity can be understood if you understand the same particles are what's making something move. They're being bent by interaction with a sea of particles.
Here, Faraday's intuitive power really shone, where at this point he imagined that a 1 over r squared force must be a...
So here's the drawing, right? And it's, so instead of understanding that the force was coming from the outside in, see, from the inside out, there's no obligation to create spheres. So that should have been a giveaway, that from the outside, you have to start with a sphere. There'd be nothing to create a sphere. If you want to create a sphere, you just do the same thing in reverse. You just have an external force going in from all directions. And it doesn't go in a circular way. It's just going in as a random way, and there's a certain random number of things that'll hit everything in space. So every spot in space is getting hit by what looks like, some sort of deliberate light bulb effect, where everything's heading right for its center of gravity. But that's just an accident of what randomness does in a field. And so all they had to do was reverse this image, and they'd have the answer. Have it going in rather than out, and they got it. So it's not even a very good drawing of randomness, but what Rutherford fell on is the idea that these are lines of force. So they're not really drawing them the way they should be drawn, as radial lines coming out of the sphere. And technically they're going in, but I'm just saying.
Be applied by something that radiated outward, like sunlight.
See, technically it radiates outward because when it goes in, it goes out the other side or it reflects. So you get the idea that the force is bouncing off of the charge. So the charges are radiating the force that reflects off them. And if you just put two colors in this diagram, so if you just change those little specks to red and black, and you only have the red ones bounce off, and you have the black ones go this way and this way, you know, two parallel directions or something, just to point out that they're not reflecting. But then you understand if you have a little more extra of one color or a little less of another color, then they'll reflect back and forth, and you'll start to see why there's repulsion and what appears to be attraction. Again, attraction isn't attraction, it's just the absence of repulsion.
Seeing even further, Faraday conceived of lines of force.
There, now, see, they call these lines of force, but those lines are not the lines of force in the sense that they're not the radial part that he just showed as the cause. They're the effect of the force. They're not the cause of the force. This is where people get confused. They think these lines are stuff flying through these lines and going places. Nothing travels on these lines. There's no force in the lines. The lines are what, when you add up the radials, this will tell you how strong the field is at any one point. Where this line is saying there's this much charge in all these locations. So I'll have to do a drawing.
Starting on positive charges and ending on negative ones.
Right, so it's just such a misrepresentation of what the lines are for.
And everywhere they went.
Alright, might as well show that. So nothing travels, these lines. The lines are a consequence of doing what Maxwell created math describing. So the idea is that something radiates a force, and the lines were basically drawn. What Maxwell basically did was make it so you drew the lines proportional to how, I didn't do that very well. I'm trying to make them all the same distance apart at some location. So at some location they're exactly the same distance apart. That means the average number of rays that would hit a point. So if you're measuring the light from a light bulb, there'd be an average number of photons that would reach these points in a certain amount of time, and they all have the same distance apart. So you pick a location that has a distance, and then you find every other location that has that same distance, and that's what the lines end up representing, is what's the force at that location. So this line would represent the same amount of force will be felt at all the points on this line, and at every point the force will be perpendicular, okay, obviously, because the line is just an extension of the line. So the force will be at this specific strength, let's say a 1.2, so everything at this point is a 1.2 force, and at every point the force is in the direction perpendicular to that line. So when they draw those lines are merely a representation of when you mix two things together, these lines cancel in a sense. Now they don't really do that. The force doesn't really mix. But if you put a test charge in there, another body in there to be hit by it, it will get hit, and it will react based on what's hitting it. So the two forces, the radial lines don't hit each other, just like two light bulbs won't hit each other, the photons. But if you put something in there, it will feel the two pressures, and it will do the math essentially, and say, I'm getting 1.2 of this, and I'm getting ep27 of that, and it'll do the math and come up with a new number for what the force is at that location where the two mix. And so that's where the line ends up doing some funky thing, like crashing. Just because the force will disappear if you're in that location, kind of thing. Alright, so back to their story. But you have to think of these lines as being a consequence of what's the force if you extend these rays from this positive and from this negative, and what's the net force at these locations, and that's what the lines represent.
Which was everywhere in the universe. They carried the power to attract and repel. And Faraday's image of magnetic forces was...
So this isn't even the usual conventional drawing. I mean, these lines are totally abstract, and you know, they don't tell you, they don't give you any information at all, because they're crossing each other, doing all kinds of things. It's just very unhelpful. But the real fact is it's the rays that create the line, and then the line's shape is decided by what else is in the field.
no less vivid than his perception of electricity. One day, Michael...
And so these lines getting very wide at the outside, the distance between the lines is basically telling you, like a topographical map, what the altitude is. So the force is very strong close, and it gets weaker and weaker and weaker, meaning the slope gets less and less and less. So there's a high slope and then the gradual lack of slope. So those are just lines telling you the slope of the force. But there's no force traveling in these lines. There's nothing going around here and going back in here, and everybody keeps doing that. Everybody keeps creating all this energy that's traveling on these lines, and these lines are just an abstraction, and they're just a way of describing the intensity of a completely different set of lines that are in the actual math. The real lines in the math are rays coming off of these lines. And again, even as these lines were, as they're understood mathematically, you measure the force by taking a perpendicular off of these rounds. And the reason why you take a perpendicular is basically because of the fact that it is a straight line force that created the lines in the first place.
So Faraday's visions would become the picture of the electric and magnetic field. But his colleagues, each far more mathematically sophisticated than he, demanded a more rigorous expression of his ideas than pure intuition. Obviously, mathematical steps had to be taken.
So this is just made up stuff. His colleagues, blah, blah, blah. There's no problem. Faraday was well respected for his contribution, and nobody was demanding he do anything else. They just hadn't figured out what the use of this stuff was yet. It wasn't like there was any problem with what he had accomplished. Everybody wasn't just waiting around for Maxwell to figure something out before they could figure out what to do with it. So that's just all nonsense.
And they were, in Germany by Gauss, and in France by Ampere. But nobody strode more gracefully through mathematics, nor understood lines of force more clearly than James Clerk Maxwell. His was the most penetrating insight into Faraday's ideas.
So again, just more nonsense. There's no penetrating insight, in my opinion. I mean, he took a bunch of other people's work and found reason to unify it as one concept. You know, there was this one thing, this electromagnetism thing. The relationship between two is really strong. They'd already discovered the relationship. That was what Faraday did. So it wasn't like Maxwell showed us some brilliant, new, innovative thing about anything. He just gave you formulas to know how much electricity it would take to make so much movement in a magnet, which is nice to know, but it wasn't like a discovery of something.
And with an enormous effort, he transformed them into the electromagnetic field theory.
Right, and it's just really a mistake. Like I said, his math is fine, but the idea of the theory that's behind it, in terms of thinking of these things as two different forces still, was a huge mistake. So in my opinion, Maxwell's only went halfway, and the mathematics still needs to be fixed because it assumes a difference between charge, electrical charge, and magnetism in terms of the actual force carrier. The force carrier is the same thing.
The four laws of electric and magnetic fields that remain as valid today.
Right, and there's nothing terribly mysterious about any of them. You know, the fact is the charge, this is a spherical argument. You know, then when you get to the B field, there's a dipole field, so the two dipoles are strong, and you can imagine that where the two poles are mixed is weak, because, well, I can draw that too, but that's the only difference. So in charged bodies, you can sort of understand that their charge is quite complete. You know, there's nothing to mess it up. So when two opposite charges are in a field, there's very little mixture in terms of something in some other location getting an equal dosage of both. And that's the only difference between a magnet and electrical force, is just the fact that the charge force can appear much larger because it's on larger surfaces, and it's, you know, all one color, where the magnet functions by having a bunch of magnets inside of the magnet. Okay, you know, it's a bunch of little magnets, little dipoles, all smashed together, and it creates the effect of magnetism, which is it's a filter, so it's going to make one end radiate more stuff from one end than the other end. But unlike charge, from a distance, the further away you get from it, the red and the blue, whoops, should have did it this way, forces end up polluting each other again. So if you're close, it's very strong, and the further you get away, it gets really weak a lot faster. So it has an R cubed relationship, where you have an R squared relationship with charge, or an R relationship if you're close enough. So, and that's really the only difference between E fields and B fields in the mathematics, is you treat them differently because they're under different strength rules. Charge goes much deeper, okay, because it diminishes much slower, where magnetism, because it is a dipole, because the two poles are separate from each other, but right next to each other. Oh, jeez. Blue, Gary. It gets weaker because you're polluting the force saying, come to me, with the force saying, I hate you. So it's doing the love-hate thing, where love and hate are separate in electrical charge. So electrical charge creates, even if it makes a dipole in something that's going to be electric, the idea is that the dipoles are all pointing in the same direction as best you can, in the sense that the part that you're only looking at the dipoles at one end of the magnet. So it's a big difference if you're at this end of the magnet looking down, or this end of the magnet looking down, or you're at this side looking in. So strong this way, you know, strong this way, but very weak this way. Unless you're another magnet. See, if you're a single charge here, so the point would be, single charge here is saying I'm repelled here and I'm attracted here. Okay, so it is going to have two impulses that cancel each other. Where if the charge is out here, it's either going to be all repulsion, I hate you, or it's going to be, if you're the opposite charge, I'm all attracted. And that's the difference between the B field and the E field. And there's, you know, it's the same exact force. It's just that the force is being created by an object that has a different configuration, and therefore is going to produce a different effect. But there's no two separate fields of anything. They don't even have a description of what this field would be. Again, it has to be this radial. They've already kind of demonstrated it has to be radial. It does cause spherical symmetry, like gravity. I mean, it just fits that, you know, it's got to be a particle force. So that's what particle forces do. Straight line forces do that. Radial forces.
They were the day James Clerk Maxwell wrote them down. The fruits of both Maxwell and Faraday's work bloomed during the Industrial Age and the electromagnetic era, but only because the seeds had already been sown by someone else in a distant land. He first made a name for himself as a printer, then an indelible mark on the affairs of state.
Yes, Benjamin Franklin.
But in his prime, Benjamin Franklin made some remarkable accomplishments in the field of science. In Franklin's day, the field of electricity, like the New World itself, was green and undeveloped. In fact, all the world's knowledge about electricity could fit into a Leyden jar. The Leyden jar was the world's first means of storing electricity, and Benjamin Franklin used it to revolutionize physics single-handedly.
It's a nice collection of, you know, a way of multiplying the current. I never saw that the particular device, but you know, they're kind of implying that this is what Franklin had, but I've never seen that. But you know, just think of the work it must have taken to create all that back then. You know,
it was with Leyden jars, not lightning bolts, that Franklin made his most important discoveries. He correctly observed that if one object has a positive charge and the other a negative charge, they will attract each other. But if both objects are positively charged, they repel each other. In fact,
right, and what should be understood is that any force is going to act on something, and so it can be either repulsive or attractive, depending on what side has more force. And then they could understand why gravity only does the attractive thing, because it can't create the charges. It can't make something that ever isn't mixed. So it's always mixed. That is, the electrons and the protons are doing the exact opposite. And until it is configured in such a way where all of its electrons and protons are oriented in a certain way, like all the magnets are lined up in a certain way so you can't see the red side of the magnet. If I take a bundle of magnets and just put them all north faces towards you, you're not going to see, okay, the red side of the magnet, and therefore you're not going to feel its effects. And it's that simple. But when something's mixed, that means all the reds and the blues are mixed up, and there's just as much red showing as there is blue showing, and therefore the only thing they could possibly do is attract, because they can't create the reflections you need to create repulsion. The perpetual, they can't add the extra energy. They can't store energy between them. And that's the nature of repulsion, is storing energy between you and another object.
Benjamin Franklin invented the very terms positive charge and negative charge. But what exactly is electric charge? And what are the factors that determine how electricity does its work?
They're implying that they answer these questions somewhere, and of course they don't.
Playing it safe with electricity means understanding a number of quantities, not just charges, but also volts and amps and fields, to name.
Yes, well, none of those will tell you what's causing the effect. And again, so, you know, it's just such a kind of cheat of the language to imply that, oh yes, we're answering the cause question, you know, and they're not answering the cause question at all.
Name just a few. But no matter which quantity is on the table, it's always taken something to get electricity started. And since 1800, one way has been the electric battery. Giuseppe Galvani, the world's first neurobiologist, started it all by asking a simple question. How can a frog's leg, without the benefit of a frog, have such a large reaction to such a small electrical impulse? His colleague, Alessandro Volta.
Yeah, it's kind of a nasty bit of crap. Anyway, you know, there's nothing really to say, but yeah, I mean, this just gave them the first idea that there's energy stored in the chemistry. And once they understood that the chemistry had energy in it that could be released with a little bit of energy, a spark of electricity.
Found the answer. And by the time he had it all worked out, he'd also invented the electric battery. Of course, the battery's come a long way since Volta made his voltaic pile, with various metals separated by the odd scrap of cloth, clay, or almost anything that was handy and moist. But although the battery could get electricity flowing, it would take something considerably more powerful to turn the wheels of commerce and industry.
Yeah, unfortunately, we really haven't improved on, basic acid batteries. It's just kind of funny that, we still haven't found a way to artificially create a mechanism that does this storage thing very efficiently. I mean, it's not the batteries aren't efficient. I just mean they do it even better.
For example, consider the roundabout progress of the Dutch. In Holland, they made profits anywhere wind rose and water flowed.
That's another thing about some of these series, that some of these is so disconnected. I mean, what you exploit as an energy source is a lot different than talking about how you convert movement into energy or electricity. Converting the the movement into electricity is a lot different, and obviously windmills just turned gears and made grinding stones turn originally. They weren't generating electricity.
And throughout the Western world, this energy source was hailed as the wave of the future. But business conditions tend to change. And change they did when the steam engine came along.
I mean, this is sort of like putting sailboats in the picture and saying, look, sailboats convert wind energy into movement. And yeah, duh. I mean, this really doesn't have anything to do with electricity and magnetism.
At precisely the same time in history, coal was being added to the equation of energy sources and industrial power. Coal proved to be more reliable than wind and easier to transport than water. But a different element would soon enter the picture of industrial power. It was electricity, and no one had a better grasp of it than Michael Faraday. He invented a device that
back
twisted
to the story.
because of the magnetic field created by an electric current. This was the world's first electric motor. But Faraday went much further.
Right, well, it really wasn't the first electric motor in a way. I mean, it, yes, obviously created some movement, but it was incredibly weak. It's an incredibly weak force because of the fact that the electricity, how the current, the motor force, what the effect actually is. So we're back to the dipole argument, and so maybe I'll draw some of this. All right. So the catch is that when you run current through a wire, so this is the wire coming out of the paper, let's say. The trick is, yes, the current comes out radially from the wire. And what's really happening, okay, in all these locations, the magnetism that's created. And the real effect is that essentially as the current flows down the wire, what it's doing is it's converting a big atom into a little atom, and then converts it back into a big atom, and then a little atom. It keeps sharing the pressure and changing the field. And so again, they're little magnets, and the idea would be the magnets have a face, a north and a south face, and so they're arranged because the cells kind of have to be next to the opposite of what they are at any one particular time. And so there's a bunch of little magnets, essentially. And the trick is they're on a round surface, generally speaking. And so the point is as they go around, they sort of have a face. And so this face facing this object over here is a little more red, and this face would end up being a little more blue, the trailing face, because they're all tipped against each other a little bit with their, as they're going this way, this end sticks out. It goes this way, then it's even, and then this end sticks out, and, as it's going around. And so yeah, there's a subtle change, constant, and it's constantly changing as the electricity goes through. It's constant. Each location constantly changes from positive to negative, as the pressure moves through the wire. It constantly changes its pressure from low to high, to low to high, low to high, or lower to higher, if you want to say it that way. So there is no real rotation. There's just a constant changing, and it's a little bit more on the negative side than the positive side, so it has a rotation to it, and that ends up being the right-hand rule. But that's all the right-hand rule is. So it's a tiny change, a tiny disproportion in the force. So if you had a little wire that you also magnetized, it will spin around, but it's only spinning because it's repelling, obviously. The net effect is repulsion, and it's a little bit weighted to one side than the other, so it keeps moving in that direction. So it's the repulsion that's the real force. The opposite field is created. So if it's, let's see how to say this one right. Yeah, it's the paramagnetic thing, but yeah, I don't know if I want to get into that. Whatever pressure it feels, it ends up turning into a mirror to that pressure. So if it feels more red, it becomes red reflective. If it feels more blue, it becomes blue reflective. So it's just constantly balancing how much it's repelling by the force that it's feeling the most. And that's why it goes round. It's just because it's repelling and it's a little bit off balance. It's a little more repulsion in one direction than the other. It's not a perfect definition, but it'll have to do. But that's what has to be understood, is the magnetic force is coming out radially from the wire. As the current goes this way, the magnetic field is going this way. It's coming out the sides of the wire.
If an electric current creates magnetism, he wondered, could a magnetic field create electricity? By way of an answer, Faraday discovered electromagnetic induction. By increasing or decreasing the current in one electric circuit, the changing magnetic field he created.
So, and what happens when you increase or decrease the current? So again, it's not voltage, it's current. And current means that the electricity is in smaller packets. So it's not that you're transferring a tremendous amount of pressure. So it's not like a really big atom and a really small atom. You're just doing a little bit of pressure difference, this size to something, that size. So there's less pressure between each interaction, but there's more interactions. And the interactions are what polarizes the atom for a minute. So the more atoms you're changing the size of, that's the current. And the more atoms you change the size of, the more little magnets you're making. So that's why you get more magnetic effect from higher currents rather than high voltage. If you use high voltage, you're not polarizing very many atoms, and the fewer atoms you polarize, that is, you make bigger, the less magnetism you have. So it's like a ferromagnetic material. The fewer they get aligned, like in a screwdriver that's not magnetized, or it's a little bit magnetized, or it's a lot magnetized. It just has to do with how many are in alignment. So current allows more atoms to be involved in the process of becoming polarized, which means they're charged on one side more than they are the other. Oh, leg cramp. Oh, it's getting better. Oh, always something.
Induced a current to flow in a second circuit. And to one man, that image would suggest unlimited possibilities.
This is where it just goes way off the
His name
rails.
was Nikola Tesla.
I mean, just silly. Why they threw Tesla in here. So there'll be no example of anything Tesla did. It's just this idea that somehow Tesla was the electric guy, you know, and he made all these contributions to understanding of electricity when he didn't make any great contributions to understanding electricity at all. He made a few innovations to 2 or 3 devices, and that's it. There was nothing elemental in his contribution. Nothing like Faraday at all. I mean, it shouldn't be mentioned in the same conversation. It's just so wrong to imply that Tesla, you know, that would be, you know, 100 years behind. Oh, sorry, this leg is. I guess I better stand up there. Take a break. Back. I don't know for how long, but we'll see. I do a lot of heavy lifting today. I guess I overstrained something or other.
An ingenious twist to Faraday's discovery, he came to America to create a vast electrical power grid and to spin like a dynamo into the modern industrial age.
Just poetic bullshit. Just didn't have anything to do with reality. It was like all the rest of the people of that era. There's great excitement. There's so much going on. This whole industrial revolution thing is happening. And so, you know, him and a million other people.
In theory, the theory of alternating current, it was smooth sailing for Tesla.
So again, he didn't create alternating current. It was already a byproduct of generating electricity. You know, this is just such fake history.
But in practice, Tesla met with the most powerful resistance on the American landscape. Thomas Edison seemed to be the force behind just about every bright idea under the sun.
I guess there's no point in playing this. We'll just get to the real point. Is that even in Tesla's own writings, well after they had gone their separate ways, Tesla still admired Edison, talked well of him. And it was only later that he got into this whole resentful thing where he felt cheated. But he never even implied that that was Edison's personal fault or something. So that was just all kind of crap. He was never really involved in the war between Edison and Westinghouse over AC current. Tesla's name wasn't even in that controversy. So I mean, all this is just kind of bullshit. So let's jump to the Einstein stuff. Maybe that's more bullshitty.
Poor student. Perhaps because the work was too hard or too easy, or because his views were too unconventional from the start.
Just more mush about, well, we'll just make up some stuff. Maybe the work, or maybe he did bad in school because he, you know, didn't like his teacher, or maybe, you know, he had twitchy disease or something, or it's just, you know, they just make crap up. Frankly, didn't do that bad in high school and college, so the whole thing doesn't mean much anyway.
For a quarter of a century, his life remained uneventful, at least on the surface. But in 1905, while working as a patent official in Switzerland, this man saw the universe more dramatically than anyone since Isaac Newton.
Yeah, just more blah blah blah, hype.
He was Albert Einstein, and relativity, his way of seeing things, changed the meaning of time and space.
Yeah, it's more, yes, and in what positive way, in the sense that they just took everything right off the rails. Just forget about, again, just pretend that you can just say something like space is bent and you've somehow explained how it happens. You didn't explain anything.
If a light switched on as a train passes, it reaches the front and the rear at the same time. Well, that's one man's opinion.
Well, we know that's how it works. So we know on the train that's what will happen, and no one's going to be able to change that. If you actually have flags on the train that go off, that will be all what will happen. One light will go on first, one light will go on second. But again, this just has to do with, again, this notion, photons always travel the same speed. That's a fact. Nobody can make them go faster or make them go slower. That can't happen. But as you move two things towards each other, obviously the amount of time that's going to take for the thing, shooting the light or even having light reflect off it, it gets to you sooner. So obviously it's going to seem like actual photons got to you sooner. But the actual photons never moved any faster. It's just they're being shot from closer locations. So obviously they get to you sooner because they're only half as far away.
But consider an outsider's point of view. In Einstein's relativity, events that are simultaneous to one observer may happen at different times according to someone else.
Right, which is just absolute nonsense. Can't happen, won't happen, doesn't happen, whatever you want to say. Can't be the truth.
And to see both points of view together requires combining space and time in a single four-dimensional continuum.
So it doesn't. You're just recognizing that photons are the stable thing and we're the unstable thing. The photons always do the same thing. We're not always doing the same thing towards them. So if we're moving towards them or we're moving away from them, obviously there's going to be a difference. If you're running away from, if there's a bull coming towards you running 60 miles an hour and you run 70 miles an hour, you'll still be getting away from the bull, okay? But if you run 60 miles an hour, 61 miles an hour, then the bull is going to be in one place and you're going to be in another place, and it's not going to seem like you're making up much ground on the bull. And it's just a fact. So the photon is always doing the same thing. We're the ones who do something different. We move towards it, or we move diagonally from it, or we move in some other way, and by moving in some other way, we're the ones who are changing the environment. So the idea that photons have a constant speed doesn't mean they have a constant speed perceptually if you're running towards them. If you run towards somebody shooting bullets at you, the bullet will hit you sooner. It's just a fact.
Looking at the world freshly, and as no one ever had,
Nonsense.
Albert Einstein saw that according to any observer at rest, a moving clock must actually run slow.
So again, this whole clock nonsense, the only clock we have proof of this happening to are atomic clocks. So the argument is that when they're moved, there's a consistent degrade in their function. But all the other clocks you can make are disturbed by different circumstances. Okay, I mean what do you call the sand thing? Hourglass. An hourglass isn't going to work without gravity. Pendulums won't work without gravity. Lots of clocks break for all kinds of reasons, or they become dysfunctional. And clearly the clocks that are running us are going to be affected in a completely different amount and at different degrees by different kinds of velocity. So there's no rule here that time changed. It's just you break different clocks. Velocity will break different clocks in different ways. Just as if I took all the clocks on Earth and I moved them, they won't all break in terms of how they tell time the same way.
And that moving rulers are contracted.
Yeah, well, that's just nonsense. There's not any evidence of that.
And for that matter, he saw much that would change human perceptions about the way of the world. For example, a set of twins, Albert and Henry, born in the same time and space, are on the surface very much alike. And yet on the inside, they may turn out as different as night and day.
Right, and this whole question doesn't mean much in the sense that if you send the two twins and one has velocity and one doesn't, it sort of breaks the whole concept of it doesn't matter who's moving and you can't tell who moved. You're clearly going to tell who moved because the person who isn't moving shouldn't be aging slower. So it's another way you can tell the difference.
Being so different.
I mean, they're just contradictions in their own theory. One minute they say you can't tell the difference, the next minute you say, well, you can't do an experiment. Well, the experiment you can do is, you know, is stick a baby on the outside of the spaceship and put a baby on the inside of the spaceship, and you know, have the spaceship, you know, 1,000,000 miles long, and you'll be able to tell because the baby on the outside of the ship is going to age less than the one inside because the spaceship's moving and the baby on the inside isn't.
And at the same time so alike, may be the ultimate paradox of identical twins. In physics, however, the twins paradox takes off with another image.
I don't even know why they're doing the twins paradox with non-twins, so that's kind of bizarre.
This is Brother Henry's first time away from Albert. His destination, the planet Zog, 10 light years away. If he could compare his clock to his twin brother's, he'd find Albert's clock running slow.
See, that part doesn't make any sense. He would find Albert's clock running slow. No, he wouldn't. He'd see it fly by, like, whew, it's gone. You know, if he has a window, he's going to see how fast he's going, unless he assumes the whole universe is flying by him. So that's the lie of this thing. You have to presume that he's in a spaceship and he has no windows, so he can't see anything. So he's just going to imagine, because he's not allowed to see anything. But if he actually could see the clock, it wouldn't be moving slower. It'd be moving faster.
And if Albert could compare his clock to Henry's, he'd find it running slow. And no matter how it looks, that spells paradox.
Right, so just quit. As soon as you spell paradox, you know your game is over, you should start over. You have the wrong answer. Paradox is a really bad answer to get.
But when it comes right down to it, what does that...
Who cares? Yes, when it comes right down to it, who cares? Paradox, paradox.
And countless other mysteries throughout the mechanical universe mean. It means a journey into the atom itself, into electricity and magnetism.
Yeah, and you can't understand them as all these swirly thingies. You have to understand them as rays, straight lines. The forces are all straight line forces. And they're all moving the same speed. And they're little tiny bits of energy that hit little tiny locations. And that's how it really works. All of this crap isn't how the universe works. All this swirly crap. No. It's about rays of force hitting things. Hitting little bits that do move, but don't move much. Atoms are just magnets. And they're monopole magnets. The charge. And they sit in locations, and that's how they connect to each other with geometry. And if they were doing all this swirly crap, they really couldn't combine. That's reasonable to understand. There'd be way too much movement going on for two atoms to actually share an electron or to stick to each other. They have to be more rigid to be stable.
Relativity, thermodynamics, and more, into a realm previously unimagined.
And better off not imagined, because it's the wrong answer. It's not how the universe works. It's not the mechanical universe. It's a bad guess. Or it's just a wrong guess. And you need a better guess. You need to think harder or better. Alright, enough of this. It's just all this woo 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 woo. I think that's all that's left here is woo. Yeah. Alright, so that's enough of a video. I got to the points I wanted to, I think. So, till the next time. And such. Yeah, I think so. I gotta do this thing.